Welcome to the workshop. Yesterday we made the flywheel heavier and that made the music tighter. Today we're going to make the flywheel faster by changing out the gears so it spins faster, which means it has more moment of inertia, which I think will make the music even tighter. The only way to access the gear is to first remove this bearing right here, and then I need to lift the whole wheel up. I'm going to use leverage to be able to make this lift. Someone said, give me a lever long enough and I'll lift the world. So that's what I'm trying right here. And it is surprisingly easy. So now I can access to change the gear. The previous pulley was 70 millimeter in diameter, and now we're trying a pulley that is 50 millimeter in diameter, which will result in a nice increase in speed and a nice increase in moment of inertia. And when I'm done, I'm putting all the bearings back, and then I can lower the lever back down, and I've actually succeeded in doing this lift safely by myself thanks to leverage. I designed the ratio between these two wheels to be kind of 1:8. So this should do 8 revolutions, while this does 1. Let's follow the tapes. So here we have 1, 2, 3, 4, have to slow it down, 5, 6, 7, and kind of 8. And this is the moment I've been waiting for, because now we're going to unleash the full power of the flywheel. Just to show you, I'm giving it my all here. I'm giving it my all. I'm really putting my whole body weight. This is how tough it is to get going.
The new flywheel setting is really tough to accelerate. Me and Hannes are building up a lot of energy into the wheel. And then I'm using a drum beat to play tight to. Previously, I only used a metronome, but I think with a drum beat, you can hear a little bit better if I'm playing tight or not. So let's take a listen to some of the best segments from the first test. Now we can use the awesome tool from Tom and Jan. I'm dragging and dropping the file onto Wilson, and Wilson calculates everything. We're looking at 100 best transients consecutive, and here's the results. The green wave is a tempo wave, but it's zoomed in now, so it looks very untight. I'm changing to 80 BPM, and then the green wave is more zoomed out. And then we can see that it actually looks tighter. And if I'm zooming in on a single transient, we can start to appreciate the wonderfulness of the similarities plot. Because check this, now we can see that one single transient looks exactly like on the similarities plot, which tells me that the software has detected all the peaks correctly. So now I can trust the standard deviation value of 4.94 milliseconds, and I can enter that into my spreadsheet. And in the spreadsheet, I made 3 measurements: 10 best transients, I looked at the 50 best transients, and at the 100 best transients. So let's increase the speed to 100 BPM and do the same thing again and compare. As I'm now pedaling faster, we have more moment of inertia and the music feels tighter in the room. Let's see in our results if the music actually is tighter, and yes. Right here between the dotted lines, we have the 100 tightest consecutive transients, and they had a standard deviation of 1.68 milliseconds. Looking in our spreadsheet, we can compare with previous tests where we had 4.94 milliseconds and now we had 1.68. which means that when we're going from 80 to 100 BPM, we increase the moment of inertia and we get much tighter music. Let's go the fastest, 120 BPM. And as you can hear, the music is really start to become tight here.
This is best. More moment of inertia, tighter music.
I've been testing for 3 days and this is by far the best feeling in the room. The music feels really tight here. This BPM curve is really cool. You can see the acceleration in the beginning and the smooth deceleration in the end when I stopped pedaling, and the plateau where I'm playing 120 BPM. And between the dotted lines, we had an amazing standard deviation of 0.88 milliseconds. By far the best I've ever measured. Let's try the crank, and it was really hard to get it up to speed to accelerate this heavy flywheel, even for someone as strong as Hannes. And we're going to try the 3 tempos, so let's listen to 80 BPM. Let's listen to 100 BPM. Let's listen to 120 BPM.
Oh, it's tight. It's horrible, but it's tight. Woo!
And now, my friends, I have all the measurements from all the configurations, all the tests I've been doing in Rudolfsheim, Germany, and we can compare and make some key takeaways from these test results. Takeaway 1, more moment of inertia equals tighter music. You can see if I break out speed that the standard deviation goes down with higher speed, and if we break out only by weight, you can see standard deviation is going down, and if I combine them, it's a big difference. Takeaway 2, more moment of inertia leads to a slower tempo wave. I call this a tempo wave, and it's the green thing going up and down, and I've been counting the peaks and how many peaks fits within the 100 best transients. And as you can see, the higher up we go on the flywheel, the less waves. Takeaway 3, crank plays tighter music than pedal. So this is expected, but a bit unfortunate. Pedal is the better option because I can put in more energy into the system with the pedal because I'm just stronger in the legs, and with the pedal I have that one extra hand to play music and operate levers with. So this is a bit bad of a result. Takeaway 4, the best setting was crank with the strongest flywheel, and we had an overall standard deviation under a millisecond, which is pretty cool. But this is actually only measuring at its best performance. We actually want a system that can play very well during its worst performance as well. And with this flywheel, I don't think we're there yet. Takeaway 5, results could be improved by increasing inertia. Takeaway 6, the crank is physically challenging to operate. Takeaway 7, the data is a bit skewed in 2 ways. So during later tests, I had more practice playing the prototype, which would skew later tests to look better. And later test was also longer, which would also skew later tests to look better. So even though we have two different things that has skewed later test results to look better, it felt obvious to me in the room that more moment of inertia was better. It was easier to play tight music. Takeaway 8, we could have a gearbox between pedal and the flywheel, because in lower tempos we have less amount of moment of inertia, but if we geared up the flywheel in lower tempos, we could equal amount of moment of inertia in different music tempos. That would be pretty nice. Last takeaway, what will be the next step? So I have two alternative routes to go from here. Either I can add more moment of inertia to the flywheel and applying the governor that was already designed for the prototype that I didn't have time to put in. And then I could see how much I can improve the results on this prototype. Or I can build a small-scale benchtop Huygens chain drive prototype with 3D printed parts and bearings, so a more serious version than this Lego prototype I built. And I think I will get more value out of building the Huygens drive first to better compare these two very different designs. And that will also be the next series on the channel. With the Huygens drive, we can separate power generation and maintenance from the speed selection for the music, and that could actually be a very good design principle for the whole project. And if we zoom out even more, I just want to say that the prototype was a huge success. All the parts functioned the way I thought they would in CAD. I think I've proven myself as a CAD designer who can CAD something and make it work in real life at first try. So that was a huge success. And if we go back to my pyramid, which is ruling my life at the moment, if you think all of this is overkill, I can just tell you, if I can't fix this first basic step 1 in the pyramid, where the music timing has to be tight, I'm not interested in doing the project. I know that designing a solution that can play tight music consistently will be the heartbeat of the whole marble machine. So I want to examine the Huygens drive before adding more moment of inertia to the prototype to better be able to compare the two. Before I leave Germany, I'm heading over to the museum to take a look at how the weight-driven machines over there have solved this exact issue. But that will be in another upcoming episode from Germany. Thank you everyone, and see you later. Ciao.